Alright, after looking at some very basic limit laws, we are going to talk about continuity, which is an important topic, and then we'll be ready to look at limits more in general in the next video lecture. Okay, so continuity, what is it? You might have heard about continuity before. One way that teachers in pre-calculus classes, or that we talk about it in pre-calculus classes, is a function is continuous if you can draw the graph of the function with your, say, your pen on the paper in a way where you never have to lift your pen or paper off of the your pen off of the paper. That's what I'm trying to say. So here's an example. I'm never moving my pencil off my paper, and so this would be an example of a function that's continuous. Okay, well, that's a good intuitive way of thinking about continuity from a graphical standpoint, but we need a functional definition, and so here it is. Now that we know limits, basically, or about limits a little bit, we can define continuity. So a function is continuous at x equal a. We say if the function is defined at a, if the limit as x approaches a of the function exists, and these two quantities are equal. In other words, the value of the function that exists in number 1 and the limit that exists in number 2 are equal. Okay, so essentially we've defined f in a way, or we're saying a function f is continuous if it's defined at a and the limit as x approaches a of the function exists and is equal to f of a. Sometimes the definition of continuity is just stated in number 3 by itself under the assumption that both of these quantities on either side of the equal sign both exist. Now let's take a look at this. I want to show you how we can have points where a function is not continuous. And when it's not continuous, we sometimes say it's discontinuous. Discontinuous is not continuous. And we talk about sometimes continuity. Is a function continuous? And if it has points where it's not continuous, we talk about those points as being discontinuities. Discontinuity is another word we use. So discontinuous means not continuous. So let's take a look at this. I'm going to look at a graph of a function at 3 different values of x, a, b, and c here. These are different values of x. I'm going to sketch the graph of this function. It's going to be kind of a strange looking function here. This is just a dashed line, just for reference. Okay, so really weird functions. You can see some holes and jumps and gaps. Certainly you see some problems as I'm drawing this graph from left to right where I would have to lift my pen or pencil off the paper to continue the graph. And so you can kind of talk about looking at that and talk about points of discontinuity. But now we can talk about it specifically in terms of this. We're discontinuous. This function is discontinuous at the points a, b, and c. So if this is the graph of the function f, it's discontinuous at a, b, and c. It's discontinuous at a. Why? Because f of a is not defined. All right, f of a needs to be defined for it to be continuous, and f of a is not defined. If I go vertically up or down, there's a hole right here. I never hit any part of the graph. In fact, x equal a is not in the domain of the function. Okay. So it's not continuous at x equal a. We've got a hole in the graph. You've got a hole in the graph, you're not going to be continuous there. Thinking about drawing that graph, I have to bring my pen or pencil off the paper and then continue to the other side. So it's not continuous at a. It's also not continuous at b. Now the value of the function does exist at b, so we do have the function defined. If I plug in, what's the output going to be? The y coordinate of this hole. whatever the y-coordinate of this hole is, whatever the height is here, that's the value of the function. That's the value of the function is defined. But what about number 2? Does the limit exist? Well, from the left the limit exists, and we're approaching this point, so it would have this y-coordinate as the limit from the left. The limit from the right, however, is going where? We're going toward this hole, so the limit from the right would exist, but it would be equal to some value that's less than the limit from the left. Since the limit from the left and the limit from the right do not both equal, right, each other, then the limit does not exist, right? And so since the limit doesn't exist at B, number 2, then we have a point of discontinuity. And you can see this is sometimes called a jump discontinuity. As we move from here to get to the rest of the graph, we have to lift our pencil off the paper, jump down here, and then continue. So there's a jump, there's a big gap here. Here at C, what happens? Is the function defined at C? Yeah, right here, this point right up here. That's the value of the function at C. Whatever the y-coordinate, come over here to the y-axis, what's that height? That's the value of the function, so the function is defined. What about the limit? Does the limit exist? Well, as I approach C from the negative side, where am I going to? I'm going right to the hole here. I'm going right to this hole, so the limit from the left exists. It's equal to the y-coordinate of this hole. The limit from the right, where am I going to? Same thing, going right to this hole. Right, so the limit from the right also exists. And the limit from the left and the limit from the right are equal. Therefore, the limit exists. So the function exists, right? The value of the function is the y-coordinate of this point. The limit exists. That's the y-coordinate of this hole. The problem is what? Those two values are what? Not equal to each other. Right? The value of the function is larger than the value of the limit. And so number 3 is violated. Okay. Now, when we talk about discontinuity, so we have discontinuities at A, B, and C. We sometimes like to refer to ones that are removable. So at A and at C, we have what we call removable discontinuities. Okay, removable discontinuities. So what's that mean? Well, we've got a problem here, right? We've got a big gap, right? But this one could be corrected by slightly modifying the function. And the way I would do that is to simply redefine the value of the function at C to, instead of being this point, to be the hole, the y-coordinate of this hole. So basically I could take this point and just pick it up, if I could, and plop it into the hole. Just put that point into the hole. That would make it continuous, right? So it's a removable discontinuity in the sense I do have to define the function, but it's only at one point. I just have to bring this point down. Same thing here. I can remove this discontinuity. Now there's no value of the function, but I can define it to be equal to the y-coordinate of that hole. In other words, take, maybe you got to stick a piece of gum, take it out of your mouth, and we'll just stick it in the hole, right? I mean, that's really what we're doing. We're fixing the discontinuity. If we can fix the discontinuity in that simple of a way by just redefining the value of the function at one point, essentially, then we're talking about removable discontinuities. Okay? Well, if these are removable, we say B is a non-removable discontinuity. Okay, non-removable. And the problem is, it is not easy to fix this problem. Right? It's not like I can just take one point and fill it in the hole or move a point. I have to do what? I need these two pieces, right, of the graph to sort of connect. I'm going to have to bend, this piece up here down, bend this piece to the right of B up, so to speak, maybe, connect them. And that's going to deform the graph of the function for a large, larger set of values, right, for many values about B, right? So it's going to deform the entire graph. So that's a problem. That's a big problem. Okay. So removable discontinuities are bad, but we'll see not so bad, because notice the limit exists. That's essentially the key. If the limit doesn't exist, then we have non-removable discontinuity. Okay. So let's take a look at some functions and see if we can determine where they're discontinuous. Here's a function g. Where is this function discontinuous? Well, clearly, the answer is it's discontinuous at x equal 2. because I can see clearly if I divide by, if I plug in x equal 2, I'm going to be dividing by 0, and that's not defined, right? That is not defined. Okay. What's the graph of this function look like then? I mean, do we have a removable or non-removable discontinuity? What do we have? We certainly do not have a point at x equal 2 anywhere on the graph. Well, it helps to simplify. Notice up top, I can factor out a 3 from the numerator, leaving me x minus 2. And what do you realize here? Well, I have that common factor of x minus 2 here, and I can simplify this down to just 3. Of course, that is what? Provided x is not equal to what? 2. Remember, x cannot be 2 in the original function, so we got to be careful that x is not 2 here. So the function g of x, what's the graph of it look like? It looks exactly like the graph of g of x equals 3 for all values of x except x equal 2. So what's that going to look like? Well, the graph of g of x equal 3 looks like what again? It's a constant function. Height is always at what? 3. Okay? But the problem is that's only true for values of x not equal to 2. And so what's happening is the height of the function is always 3, right? Always 3 until what? Right here at 2, what do we have? A hole. So the graph of g of x, 3x minus 6 divided by x minus 2, that's what the graph looks like. There's a hole right at x equal 2. But the limit exists, right? As we approach 2 from both sides, where are we going to? We're going right to that hole. So the limit exists, it's equal to 3. Right? The limit still is 3. But the problem is the value of the function doesn't exist there. There's no point. So it's kind of like this a situation here. Let's look at number 2. Now, let's see. This function is a piecewise defined function, right? If x is not equal to 0, then it's equal to the function sine of 1 over x. Now 1 divided by x is fine as long as x is not 0, right? Which is the case here, which is good. So this is always a real number. And sine of anything, well, that's a real number. And if you think about the sine function is, think about it. Do you ever have a point where in the sine function where you have to lift the pen or pencil off the paper? No, it's going to be continuous just about everywhere. As long as you're plugging in a real number, you're going to have a continuous function. And we'll talk more about that later. The problem then is right at 0. What's happening? Because if x is not equal to 0, we're equal to this. But if x is equal to 0, we're equal to 1. So notice that g of 0 equals 1. But the problem is, what is the limit as x approaches 0 of sine of 1 over x? Well, if you watched our video when we were talking about finding limits initially, numerically and graphically, we looked at this one at the very end of that set of videos, and we saw this particular function, sine of 1 over x, it's not defined at 0, but as x gets closer and closer to 0, this function begins to wildly oscillate between 1 and negative 1 an infinite number of times. And remember we said that it's simply the limit does not exist. Right? It keeps bouncing back and forth between 1 and negative 1. And so we are not continuous. This function is discontinuous at x equals 0 because the limit doesn't exist. Anywhere else, I take the limit, it's going to exist for any value of x not equal 0 because we know the sine function is not going to have any holes or gaps or jumps or anything. Let's take a look at this situation here. This time it's very similar to here. Instead of sine of 1 over x, though, it's sine of x divided by x, and that's different. Notice here I have g of 0 equals 0, but when I take a look at the limit as x approaches 0, this time of sine x over x, what's that? Well, this one we also looked at in the video on finding limits numerically, and we did a table of values, and we showed that this limit apparently is approaching 1. Even though it's undefined when x is 0, the graph of the function is trying to obtain a height of 1. The limit is 1. So the limit exists at 0, and the value exists at 0. But notice the value at 0 is 0 by the definition, but the limit is 1. Since these two values are not equal, we are discontinuous at x equals 0 again. At x equals 0. Now, for any value of x not equal to 0, sine x divided by x is going to be defined. And if you think about those functions, there's no holes or gaps in any of those. It's going to be continuous everywhere else. Now, I could make h of x continuous everywhere by doing what? Changing the output at 0 to from 0 to what? To 1. So notice here, now, h of 0 is now defined to be 1, and, I'll say instead of but, I'll say and, the limit as x approaches 0 of sine x over x is 1. These both are equal, and so at 0 we are now continuous. And so this is continuous everywhere on its domain, which is all real numbers. There are no points of discontinuity for this function h of x. So it's basically the same as this one, except we plug in. So this one has a discontinuity kind of like, this one, it was removable. The limit was something, the value of the function was something else, but we fixed it by basically kind of put that point back in there by defining the output instead of being 0, letting it be equal to 1. That makes it continuous. All right. I want to talk about the concept before we go into finding continuous, where a function is continuous on an interval. I want to talk about continuity from the left and from the right. And so we are going to be left continuous at x equal a if the limit as x approaches a from the negative side of the function is equal to f of a. Now what that's going to look like is, in this case, all right, the function has to exist at a. So that means at a there is a point, right? There is a point. So f of a will be the y coordinate of this point, right? So f of a exists. But the limit as we approach a, what? From the negative side of the function has to be equal to this. That means as I come from the negative side, that's from below. From here, wherever the function is, I've got to be going where? Got to be going right to that point. So it's got to look like this. From the left. If I'm left continuous, I'm approaching it from the left. Well, similarly, we have right continuous. In that case, what are we looking for? There, we have, again, f of a is defined, but the limit from the right, as we approach from the right side, we're going to go right to that point. So here's continuous from left, continuous from right. Obviously, if we put these together, merge them together, what do we have? We have continuous, right? So if a function's continuous at a point, it is both left continuous and right continuous. But sometimes we're only left continuous, sometimes we're only right continuous. Other times we're not continuous at all, and that's fine, without either one of these left or right continuity being true. All right, let's sort of summarize everything here then with this graph of this strange function again. Got lots of holes. I'll just emphasize these holes and points, jumps, gaps, and other stuff. So let's summarize what we've learned so far. First of all, let's just do some pre-calculus. What's g of negative 2? This is easy, right? Input negative 2, where's the output? Got 2, well, that's a hole, that's a point, that's what we're going to use right here, so the output is 1, right? G of negative 2 is 1. G of 0, what's g of 0? Well, input 0, output what? 5. G of 0 is 5. What's g of 1? G of 1 is what? That point right there, which has a height of 2. What is g of 2? G of 2 is what? Where do we go? To the point right here, right? Which has a y coordinate of 1. Okay? So that's pre-calculus. What about limits? What's the limit as we approach negative 2 from the negative side? So here's negative 2. We're approaching it from the negative side or from the left. So where are we? We're on this curve. Where are we going? As we get closer and closer to x equal negative 2, where are we going? We're going to that hole, which has a y coordinate of about what? Maybe 3.5, right? So that appears to be 3.5. What's the limit as we approach -2 from the positive side? Okay, so now here's -2. We're approaching from the positive side. So as we approach -2 from the positive side, we're going to this point here, which has a y-coordinate of 1. So what is the limit as x approaches -2? Answer, it does not exist. Why? Because the limit from the left and the limit from the right are not equal. And you can see clearly the limit doesn't exist. We've got a break in the graph, right? We've got a huge jump discontinuity. Okay. What's the limit as x approaches 1? What's the limit as x approaches 1? We know that g of 1 is 2, so does that automatically tell us that the limit must be 2? Because g of 1 is 2. So is the limit as x approaches 1 equal to 2? No. The limit, remember, as x approaches 1, I don't care what the value of g of 1 is. This says let x be anything except 1, right? Get closer and closer to 1. What are we getting closer to? And you can see clearly, as I get close to 1 from above, I'm going to what? This hole right here. Same thing from below. I'm going right to this hole. As x gets close to 1, I'm on this function getting closer and closer to that hole, which has a y-coordinate of what? 4. The limit as x approaches 1 of g of x is 4. It is not 2. And so where do we have points of discontinuity? Where is the function g discontinuous? Well, we know it's discontinuous at -2 because, why? The limit does not exist. So it's certainly discontinuous at -2. It's also discontinuous at 1. Why? The value of the function exists. G of 1 is 2. The limit exists. It's 4. The problem is what? These two things are not equal. Since they're not equal, it is discontinuous at 1. And then what about at 2? Again, what's the limit as x approaches 2? It does not exist, right? So again, same thing. It's not going to be continuous at 2 either. Okay. Now, let's talk about the last two things. Where is this function going to be right continuous? Well, let me say specifically, of these values where it's discontinuous, where is g right continuous? The reason I say that is because it's only discontinuous at these 3 points, right? -2, 1, and 2. That means everywhere else it's continuous. It's continuous for all values, say, less than -2. And remember, if you're continuous, you're both right continuous and left continuous. So we wouldn't want to look at any of these points. We know it's left and right continuous everywhere where it's continuous. So the only question is, it's discontinuous at -2, 1, and 2. Can it be right continuous or left continuous at one of these points? It may be. We need to check. So let's see. Are we right continuous at any of these 3 points? Remember what right continuous looks like. Right continuous, right? We're approaching from the positive side, so we're coming from the right to the point. Where are we coming from the right to the point? At -2, 1, or 2. Well, let's see. At -2, we're coming from the right. Where are we going to? We're going right to the point. The limit as we approach -2 from the positive side was what? 1. What's the value of the function at -2? 1. Notice these values are equal, and so we are right continuous at -2. Are we right continuous anywhere else? At 1 or 2 rather? Well, no. As we approach 1 from the positive side, where am I going to? I'm going right to that hole, right? So the limit as I approach 1 rather from the positive side is 4, but the value of the function is 2. So it's not right continuous. Same thing here. As I approach 2 from the positive side, I'm going to -1, but the value of the function at 2 is equal to +1. So we're not right continuous at 1 or 2. Are we anywhere of -2, 1, and 2? Are any of these points, are we left continuous? Are we left continuous? Left continuous, remember, looks like this. We're approaching from the left and going to the point. So of these 3, where are we left continuous? Are we left continuous here at -2? No. We're going to this 3.5 right from the left, but the value of the function at -2 is equal to 1. So we're not left continuous. How about here? As I approach from the left, I'm going to this hole, which has a y-coordinate of 4. The limit from the left is 4. The value of the function at 1 is 2. So we're not left continuous there. Here, though, as I approach 2, from the left, where am I going to? Right to that point, which is 1. That is also the value of the function at 2. It's also 1. And so we are indeed left continuous at x equal 2. Okay, so that's the basics of continuity. Now we're going to extend this in the next video to how we can talk about intervals of continuity.